Alright, hello and welcome back to Probabilus. So, our schedule got a little bit mixed up this week, but we're back and we're ready to go. So today we will be discussing some physics content. So even though today is not a Monday, we will still be going through the physics content. And then this coming Monday, we will still be doing physics content. So this is sort of just to fill in the break that we had. So yeah, I don't really think there's much else to talk about. Today's lesson should hopefully be pretty short. With that said, let's just get into it. Here we go. Okay, so this is lesson 4 for physics, and we are talking about forces today, and in particular, we are talking about friction. So in the last lesson, we introduced forces. We learned about the normal force, we learned about the force of gravity, and we discussed tension. This time, we're going to be focusing on friction, and friction is probably a concept that a lot of you are familiar with. This is a very common English word, and we think of friction, at least when I think about friction, I think about surfaces like rubbing together. Like if there's low friction between two things, they slide across each other very easily, but if there's high friction, it takes a lot of effort to slide those two things against each other. So maybe that's how you know friction, maybe there's other definitions, but today we will be defining it in a physical sense, in terms of physics, and we'll do some calculations with friction as well as some other forces. So let's get into it. And as always, we'll start with our little bit of like lecture review just about friction. So, as I kind of alluded to, friction is the force resisting the relative motion of surfaces. So I mentioned surfaces sliding against each other, but friction is the force of resistance between those two surfaces. And that sort of makes sense, right? If you're trying to push something across, like on the ground, there is friction between the object you're pushing and the ground, right? There's still two surfaces. But it's not always so easy to push something on the ground, because, well, maybe the object's really massive, or the ground is rough and it's hard to push it. So that force is actually resisting the motion that we are applying to it. So if I'm pushing in one direction on the object, friction is pointing in the opposite direction. The opposite direction of motion. That's going to be very important when we do our questions. So there's two types of friction. There's kinetic friction and static friction. So kinetic friction is the friction between two surfaces when they're in contact and moving. So that's the example of me pushing something across the ground. It's moving because I'm pushing it, but it's still in contact with the floor, and the floor is providing that resistance. So that's kinetic friction. Static friction is a little bit less intuitive, maybe, but this is the friction between two stationary objects. But that should sort of make sense, right? Think about just like anything sitting on your desk right now. It is in contact with the surface of your desk. But certain things have higher static friction than other things. For example, it might be really easy to slide a piece of paper on a desk because maybe the friction is really low. But if you consider a mouse pad, for example, that it's much harder to slide across the desk. But the mouse pad stays on your desk because there's friction between the two surfaces. It's not moving right now. That mouse pad is not moving, but there's still friction, and that avoids it from sliding all over the place without us even touching it. So the good news is that even though there's two types of friction, the equations are very similar. So first is the equation for static friction, and that says that the force of static friction is less than or equal to this term mu sub s times F sub n. So we're familiar with F sub n. We saw that last time. That's the magnitude of the normal force. So that should sort of make sense, right? Because we're discussing two surfaces, maybe one on top of the other, and we saw that there's a normal force when one object is placed on top of another surface. So that's good that we see that in the equation. But then we have this mu sub s term. So this is the coefficient of static friction. Okay, what does that mean? Basically, all materials have this coefficient of static friction, and all it is just a number, like 0.2 or 0.05. And that number tells us basically how much friction does that surface have. So a low value for this coefficient of static friction means that it has a low amount of friction, so it would be easy to slide something across it. Something with a higher coefficient of static friction, well, it would be like harder to move. And then we move down to this other equation down here, where this is saying the force of friction for kinetic friction that is equal to mu sub k times F sub n. So F sub n is still the same normal force we've seen. Mu sub k is also a coefficient of friction, but this is the coefficient of kinetic friction. So very similar to the coefficient of static friction, except one relates to stationary objects, the other one is for moving. Yeah, so typically our coefficient of friction, almost always it's below 1. I wish I had like a graphic showing like different materials and their coefficients of static friction, but for the most part, a lot of objects have their coefficients of friction pretty low. I'm gonna see if I can pull something up. Coefficient of friction for, let's just say, wood. So wood on wood, meaning you have two surfaces, because we're dealing with friction, and they're both wood. The coefficient of static friction is between 0.25 and 0.5, and for kinetic friction, it's 0.2. What about glass on glass? That has a higher coefficient of static friction at 0.94, which is actually really high. And for kinetic friction, it seems like it's 0.4, which is quite a bit lower. Is there anything else that seems interesting that I can share? Yeah, let's do ice on ice. That seems like it would have a really low coefficient of friction, because it's really easy to slide ice on ice. Think about like an ice rink, and you can just like imagine shoving a block of ice on that ice rink. It would probably slide very easily. And that is true. The coefficient of static friction is 0.1, and kinetic friction is 0.03, so extremely low. So we see that for the most part, these values are less than 1. Cool, so those are the equations that we use for friction. And that's basically all we need to know for frictions. We can already jump into the problems. So that's in fact what we are going to do right now. So this is the first question, and we're dealing with this inclined plane. So we have a block, and we want to find the acceleration of the block if the angle of incline is 30 degrees. So I'm just gonna mark that here. And the coefficient of friction is 0.2. So we have mu equals 0.2. But before we do that, we should draw a free body diagram. Okay, so I'm just gonna sketch the surface that we're working on. So that's like the incline, and the dot is in like the center of the block, right? That represents the block. So what are the forces acting on this? We have gravity pointing downwards. And we know that the block is sliding down the incline. It wouldn't slide upwards, that would be kind of weird. And there's friction. We're given that there's a coefficient of friction. And given that we just learned that friction opposes motion, the force of friction would actually be to the upright. So friction points in this direction, backwards, and I label this as F sub F. But there's actually one more force that we have to consider, and that's the normal force, right? Because the block is on a surface. So in which direction is the normal force pointing? Well, most of the times we make it point upwards, but that's only when the object's on a flat surface. Here, actually always the normal force is perpendicular to the surface. So the normal force looks something like that. So that's our free body diagram. And it looks kind of weird, right? Because the force of friction is at an angle and the normal force is at an angle. What I mean by angle is when we look at our normal coordinate axes, right? FG points downwards, but FF and FN are kind of off, and that seems like it's really annoying. Also, the direction of motion is at an angle, so that's very, very annoying. So what we typically do for these inclined plane problems is we shift our axes. We rotate our axes. So what we're going to do is we're going to say that, okay, this is our new axis, and the other axis should be perpendicular to it. So now, let's just say that this is the x-axis, and this is the y-axis. So now our inclined plane follows the same incline as this x-axis. We've just sort of shifted our gaze a little bit. So now I'll redraw the forces. So we still have FG pointing downwards. We have FF opposing the direction of motion. So that's, I don't like that color. Let's use purple. So that's this direction. Let me just make it a little thicker. Right? And now we see that it's on the coordinate axes, right? It's on that x-axis. And then we also have the normal force, which now happens to be on the y-axis. Great, so we have two forces now on our axes. We have FG off of our axes, but this is good because now the direction of motion is in the direction of one of our axes. It's along the x-axis, and that's going to help us out a lot. But this is just part A, so let's see what part B is. Well, part B is literally solving the question. So, let's do that. Okay. So, what do we normally think about? We think about summing the forces in some direction. So if I draw our adjusted coordinate axes, it looks something like this, where this is the x direction and this is the y direction, right? And now, what color do I want to use? Probably not white. Let's use this green and thicken it a little bit. So the biggest issue is we have this FG pointing downwards, right? We have FN here, which is fine. We have FF here, which is also fine. But ideally, we want to do some of the forces in the x direction, and that equals mass times acceleration in the x direction. Similarly, we might want to do something like this. So to do this, we need the components of FG. So let me just switch colors, and what color do I want to use now? I suppose this purple will do. Okay, so what we want is we want FGX and we want FGY. We're splitting it up into the components. So let's just look at that off to the side. So we have something like this is FGX, this is FGY, they're perpendicular to each other, and together their vector sum creates FG. And it seems like we need to use some sort of triangle stuff here. There's a right angle there, and well, we know that this angle here is 30 degrees. So can we use that somehow? And the answer is yes. If we, these colors are gonna be very difficult. So we see that FG is perpendicular, so we can draw that perpendicular all the way to the surface. And if we look at the hypotenuse here, this forms like a right triangle. So this here is 60 degrees because we have a 30 degrees, which means that this up here is 60 degrees, which means that this angle here with the 3 that I just wrote, that's 30 degrees. So let's zoom in here. This we know is 30 degrees, corresponding to what we just did over here. Okay, so now that we have that, we can do a little bit of trigonometry and figure out what actually is going on. Let me switch to black. I'll change the thickness. Okay, so let's just see what happens if we take the sine and cosine of this angle. So I'll just let it be theta for now. So sine of theta is opposite over hypotenuse. So the opposite to this angle is this, and this is congruent to this vector up here, which is fgx. Alternatively, we can see that this is also theta because interior angles are congruent, and then the opposite of that is clearly fgx. So this is fgx divided by the hypotenuse. In that case, well, in both triangles, the hypotenuse is this fg. So we can simplify that a little bit, and I'll just solve fgx, multiply by fg on both sides. We get fg times sine of theta, and I'll just put in theta is 30 degrees now. Let's take the cosine. So it's adjacent over hypotenuse. So this is our angle. The adjacent side to that is fgy. And then the hypotenuse is still the same. It's still fg. Right? So we can multiply again by on both sides. Fg times cosine of 30 degrees in this case. Cool. So now we have our... I'm going to draw a new free body diagram just to make things a little bit cleaner. So our force of friction remained the same, right? That was along the axes, and I'll just draw our axes here, right? Our normal force, that stayed the same. We didn't touch that. Now we subdivided the force of gravity into fgy and fgx. So now everything is on the axes, it's good. Now we can sum the forces in the directions, right? So let's do that. Sum of fx equals max. So why am I doing the x direction first? Well, really, it's because that's the direction that's most interesting. The object is moving in the x direction. That's the direction in which the block is accelerating. We can kind of infer that the block is not accelerating in the y direction because it's not flying up and down off of the inclined plane. It's staying on the plane, so it's not changing its y coordinates per se. It's only the x position that's changing. So really, I'm trying to solve for ax, right? That's what we're trying to solve for, the acceleration. So that's why I'm using this equation first. So what are the sum of the forces in this direction? Well, let's see. We defined, we let this be x. I'm just going to say that this is the positive x direction, and then negative x is over here. So if we do that, then we have fgx minus ff equals max. So we're getting a little bit closer there. And well, we kind of already know what fgx is, and we kind of know what ff is. Fgx comes from what we just computed with the sines and thetas. So that is fg sine of 30 degrees. And by formula, ff is mu times f sub n. And we're saying that equals m times ax. Okay, just gonna do a quick simplification here, get rid of this fg. We know that equals mg. So the left-hand side goes to mg sine 30 degrees minus mu times f sub n. Okay, we're getting close. We were given, it's a little hard to see, but inside the block it said 3 kilograms. We can see that up here. So we're given mass, we know what gravity is, we know sine 30 degrees, we know mu because we're given the coefficient of friction, we just need to find this Fn because we're given mass, and that will help us solve for acceleration. So what is Fn? Well, Fn is pointing in the y direction, so let's just see what happens when we take the sum of the forces in that direction. Right, may. And as I said, the block isn't accelerating in the y direction. It's not jumping up and down. It's just sliding along in the x-axis. So that means there's no acceleration in that direction, so the sum of the forces should be 0. So we had up here, I just made that the positive y direction, so that means down here is the negative y direction. So we add all of the forces pointing in the positive direction, and then we take away the force pointing in the negative direction, and that equals 0. This acceleration is 0. So that tells us that Fn equals Fgy. And we solve for Fgy. We said that equals Fg times cosine of 30 degrees, and just a quick simplification there, gives us mg cosine of 30 degrees. Alright, cool. So let's substitute that back in. So I'll copy this and paste that here. And that tells us that now we have mg sine of 30 degrees minus mu times mg cosine of 30 degrees equals max. And now we can factor out or divide by m on both sides, and we'll get ax equals mg sine 30 degrees minus mu mg cosine of 30 degrees. All of this divided by m, and we see that there's a common factor of m in here, so this is simply g sine of 30 degrees minus mu g cosine of 30 degrees. And well, we can just plug in values now. 9.8 sine of 30 degrees minus 0.2 is the coefficient of friction given to us, 9.8 cosine of 30 degrees. And if we compute this, we should get 3.20 meters per second squared. Cool. That's actually really cool. We're really able to solve these kinds of problems with less and less information. Like this time, all we knew was the mass of the block, the angle of the incline, and the coefficient of static friction, and we already know what acceleration it'll be experiencing. So I think that's pretty exciting. So yeah, that is our first question, and we'll just move along. And we're hit with a multiple choice question, the favorite of many, including myself. So, a block of mass m is accelerated, okay, accelerated, that seems important, across a rough surface. Usually when we see the words rough surface, we think that, okay, there is friction present, by a force of magnitude F that is exerted at an angle phi with the horizontal as shown above. Okay, so someone's pulling with this force F, and there's this angle phi made with the horizontal. The frictional force, there it is, on the block exerted by the surface has magnitude F. Cool, so we're given that here, and notice that it's pointing to the left, which makes sense because someone's pulling it to the right, so the block is moving in this direction. So friction opposes the motion. And now we want to find the acceleration of the block. Alright, well, this seems similar to what we just did. We'd probably want to do something about summing the forces in each direction, but before we even think to do that, we should probably define what our direction is. So let's say this is the positive x direction, this way, negative x, positive y is up here, and then negative y is going down, right? Something like that. Okay, so let's draw a free body diagram. We have our block. It's on a surface, but first it always experiences Fg. And like I said, it's on a surface, so there is a normal force. And this time it's pointing straight up because the surface is flat. There's a frictional force opposing motion, so that's pointing towards the left, something like that. And then we have this new force F, and if we draw in the x-axis here, there is an angle phi that it makes. So it seems like we want the components of F. So how do we do that? Let's just zoom in a little bit, and I'll drop this perpendicular here, and we can see that, okay, maybe I want to create, what color do I want to use? I want to create this FGX and this FGY here, right? So that way this is like similar to what we did before. Right now I'm just solving it on top of the free body diagram, which is not a good idea, but for the sake of space. So let's see what happens when we take the sine of phi. Well, sine opposite, so opposite of this angle is this side, and this side is the same as this, so that gives us FGY. Hypotenuse is F, so that's pretty simple. So that tells us that FGY equals F sine of phi. Similarly, we take the cosine of the angle. The adjacent of this angle is FGX here, so that's FGX, and the hypotenuse is the same, so that tells us that FGX equals F cosine of phi. Cool. So now we can sum the forces in the direction. And which direction should we do? Well, I'm thinking the x direction, because that's the direction the block is moving in. So, sum fx equals max, and we're trying to solve for ax. So, forces pointing in the positive direction, fgx. That's it. Forces pointing in the negative direction, ff. Subtract it, that equals max. Okay, so that tells us that ax equals fgx minus ff, all of this over m. Okay, and if we look at the answer choices, it's not really any of the answers yet, but luckily we can make a substitution because we know what fgx is, right? We just computed it here. So let's make that substitution, and we'll get that ax equals f cosine of phi minus ff over m. I used f sub f to denote friction, but they just use a lowercase f, so just to match their syntax, I'll change it a little bit. So that's our answer, and we see that, oh wow, that is choice D. So that was a nice and simple multiple choice for the most part. Yeah. So notice how whenever we see these forces at angles, we want to split it up into the components. Now, maybe you're questioning that, wait, in the last example we shifted our axes. Why didn't we do it this time? Couple reasons for that. First, and most importantly, in the previous example, we shifted the axes so that way the direction of motion was along one of the axes. It's really helpful when that's the case, because then when we take the sum of the forces in the x direction, the direction of the acceleration vector matches the direction of motion. So if we went back to this example here, like, let's just say we solved the question using this coordinate axis, where this is the x direction and this is the y direction. And let's say somehow we figured out the acceleration in the x direction. Well, then we still have a problem because the acceleration vector is pointing in one of these directions, but the block is traveling this way. So we would have to like separate the components of acceleration, which would be really annoying. So we shifted the axes in this example, so that way the direction of motion followed an axis. In this example, the block is sliding to the right or to the left. In this case, it's moving to the right, but it's on this flat surface, so we kept the axes how they were. Also, another reason, though it's kind of a worse reason, is that here we have three vectors pointing in directions that are already established by our axes and only one that's not. So if we shifted it, then we would have to do components of three vectors. And it still would have worked, but then our acceleration vector would have been pointing in this direction or that direction, when in reality we wanted to point it in one of these directions because that's how the block is traveling. Okay, hopefully that explanation made sense. Let's move on to question 3, and we got a really nice graphic for this one. It's not quite December yet for the holiday season, but it's close enough. So we have a reindeer pulling on a sled at an angle of 20 degrees above the ground, okay? The sled has a mass of 30 kilograms, that seems important. Coefficient of friction between the sled and ground is 0.3. What is the minimum force the reindeer needs to exert so that the sled moves? Okay, this seems like a new kind of question, but I assure you it's very similar to things we've done before. First, 20 degrees above the ground. Let's just sort of label that. So the ground is that kind of parallel thing, and so this is 20 degrees. This is 30 kilograms, and mu equals 0.3. Okay, so what is going on here? What do we need to do? This seems a little bit complex. Well, let's start how we always do, free body diagram. So let's look at the sled, because that seems the most important, right? We're given the coefficient of friction between the sled and the ground. The force is being applied to the sled by the reindeer. So that's our sled. We're on it's a sled, so gravity points down. We're on a flat surface, so normal force points upwards. We're moving in this direction because that's where the reindeer is going. So friction points to the left because it opposes motion. And then the reindeer has this FR thing here. So this seems very similar to what we just did because this is at an angle of 20 degrees. So let's break it up into its components. This is FRX. This is FRY, fry, and then we have our little triangle thingy here. Now remember, let me just go back here. When we break it up into the components, in this case we broke it up into FG, I don't know why I use G's. It's not supposed to be a G. I guess I was just still in the mindset of the first problem, but these G's should not be here, nor should they be here or there. So that's my bad. But when we break the force into its components, when we sum the forces, we do not take into account the vector that's at an angle. We only take into account its components, because the vector sum of those force components creates this vector. So in the diagram, I would erase this force vector, right? Because I've shown its components now. So that's the new free body diagram. So we'll do a similar thing here, but I'll keep FR in for now just so we can compute FRY and FRX. So sine of 20 degrees, we'll do opposite over hypotenuse. This is the opposite, so that's FRY. Hypotenuse FR, so that tells us FRY equals FR sine of 20 degrees. Hopefully this is feeling much more comfortable, this component stuff. The adjacent side is FRX, so this gives us FRX equals FR cosine of 20 degrees. So now that we've broken it up into its components, let's just get rid of FR, so that way we have just the components. And let me get rid of these dotted lines as well. So that's our modified free body diagram. Okay, so now we can start to think about summing the forces in a certain direction. So let's just say this is the positive x direction, this is the negative x direction, positive y direction, negative y direction. So first we should be thinking what is the direction of interest, and it should be clear that the x direction is the more interesting direction. So, let's do it. sum of the forces in the x direction equals max. The force pointing in the positive direction is frx, and then we have one force pointing in the negative direction, which is ff, and that equals max. So now this is where things get a little bit interesting. We're asked to find the minimum force the reindeer needs to exert. So we want to find Fr so that the sled moves, it begins to move. So we want the acceleration to be just over 0. If it's 0, then it's constant. We'll just assume that it starts from rest. It's not traveling with some velocity with no acceleration. But we want the acceleration to be just over 0. So we want frx minus ff to be greater than 0. Okay, well, we know what frx is, we just solved for that. Fr cosine of 20 degrees minus ff is mu times f sub n. We want that to be greater than 0. But what is f sub n? We need that to compute fr. Well, to get f sub n, we'll sum the forces in the y direction, and that should equal m times the acceleration in the y direction. But the sled isn't moving in that direction, so this is 0 because there's no acceleration. So what are the forces pointing in the y direction? Well, we have Fm pointing in the y direction, and we have Fg pointing in the y direction, in the negative y direction, and that's 0. But wait, we forgot about the Fry, so we have to include that in there. So Fry is also included in the positive direction. So I did that on purpose to show that it's very easy to forget your forces. So make sure you're checking all of your forces. So let's solve for Fn. That's equal to Fg minus Fry. So that's equal to Mg minus Fry we solved for. That's Fr sine of 20 degrees. Cool, so now we can substitute. We get Fr cosine of 20 degrees minus mu times Mg minus Fr sine of 20 degrees. That should be greater than 0. Okay. And then I'm just gonna add an extra page. And then we'll copy this a little bit so we can do a little bit of algebra. It's not too bad though. So we have this. Let's just multiply things out. Fr cosine of 20 degrees minus mu mg minus mu fr sine of 20 degrees. It's greater than 0. We're solving for fr, so let's isolate those terms on one side. So we'll do the left side. So the first term stays, and the third term stays because those have fr. And then we just add mu mg on both sides. So now we can factor out this fr term. So that gives cosine 20 minus mu sine of 20 degrees. And still that's greater than mu mg. And finally we can say that fr is greater than mu mg divided by cosine of 20 degrees minus mu sine of 20 degrees. And, well, we have values for all of those quantities, so we can just plug those in. Mu we were given was 0.3. The mass of the mass of the sled was 30 kilograms. Gravity 9.8 divided by cosine of 20 degrees minus mu is 0.3 sine of 20 degrees. And if we compute that all out, that should give us 84.6 newtons. And that's our answer. So our reindeer should hopefully be pretty strong, because that is a very heavy sled. So yeah, hopefully Rudolph has been working out. Yeah. If not, they can hit the gym before December rolls around. So yeah, that's that question. And it's it's quite common that we'll see questions asking the minimum force needed so that way something begins to move. Common question, so that's why we did one of them. Alright, another multiple choice, yay! We have 3 blocks, 3m, 2m, and I guess it's supposed to be m, so I guess that's a typo, are connected to strings A, B, and C as shown above. They are pulled along a rough surface by a force of magnitude F exerted by string C. The coefficient of friction between each block and the surface is the same. Which string must be the strongest in order to not break? Okay. Interestingly, even though we've been talking about friction, and we've been focusing on friction a lot, and they've been giving us information about friction, it's kind of a red herring. We're really considering tension in these strings. And, well, this string A is only pulling this 3 mass, or 3m block, right? Because the thing is going to the right, so the only thing that's to the left of it that this string A would be pulling is this 3m block. For B, it's pulling both this 2m and this 3m block. For C, it's pulling all 3 of them, right? So C is pulling the greatest amount of mass, so it makes logical sense for that one to need to be the strongest, and that in fact is our answer. I'm sure we can do this with some more computations with friction and stuff like that, but this is really to show that sometimes we don't need all the information in the question to solve it, and we can sometimes use our intuition here. And intuitively this makes sense. C is pulling the most weight, so it should probably be the strongest, and that's the case. So yeah, we got a nice little question here where I didn't have to write anything. This question, however, will require a little bit more writing. So we have 2 blocks on top of each other, m and 2m, and there's a force pulling it to the right, and it's being applied to the large box, but both boxes accelerate to the right with the same acceleration. We're given that the coefficient of friction between all surfaces is mu, and then it's asking what's the force accelerating the smaller mass. Okay, the interesting thing here is the force of friction between all surfaces is mu. So clearly there's a force of friction this way, right? Because it has to oppose motion, and the blocks are moving to the right. But also, there's a force of friction in between these 2 blocks. There has to be, otherwise the mass m would just fly off of the 2m mass. There has to be that frictional force holding it onto the 2m block. So there's 2 frictional forces there, and the coefficient of friction between them, all of them, is mu. But remember, friction also depends on the normal force. So first, let's consider the system as a whole. So let's say this is equivalent to one supermassive block, and that's being pulled to the right with some force F, and now there's only this one force of friction here. So if we sum the forces in the x direction, that'll give us the acceleration of the system in the x direction. So yeah, so we have F pointing in the positive x direction, and FF pointing in the negative x direction, right? So here we're trying to solve for the acceleration of the system as a whole. Okay, so this can be simplified to F minus mu times F sub n equals max. Well, to compute F sub n, we need to sum the forces in the y direction. So in the y direction, we have Fg pointing downwards, Fn pointing upwards, right? And it's not accelerating in that direction, so the sum of the forces should be 0. Fn minus Fg equals 0, Fn equals Fg equals Mg. So if we take this, do some substitution, we get F minus mu Mg equals MAX. Should probably change this to be a capital M. Right? That's just what's going on there. Yeah. So what is capital M? Capital M is lowercase m plus 2m. Because we combine these two blocks into one supermassive block. So the masses should add. So that's 3m. Right? So let's just substitute that in. Minus 3 mu mg equals 3max. And now we can just solve that the acceleration of the system is f minus 3 mu mg all over 3m. And that simplifies a little bit. F over 3m minus mu g. Okay, so we've solved for the acceleration of the system, which is also the acceleration of each of the individual blocks because they stay on top of each other. So we're curious about the smaller mass and what is the force accelerating the smaller mass. So we want the net force on that object, the smaller mass, right? So we want F net on block M. Well, we know that F net equals ma, right? The mass of the object times its acceleration. And thankfully, we just solved for acceleration. So this is m times F over 3m minus mu g. That is F over 3 minus mu mg. And luckily, that is an answer choice A. So that is the answer to that question. I probably shouldn't have added the extra page. I could have fit it in at the bottom, but it's okay. We all make mistakes. Yeah. So in this question, we learned a new technique where we have multiple blocks and we consider the system as a whole and use that information to the individual counterparts. Alright, making good progress today, but still quite a bit more work to be done, so let's move on to this next question, and it's another multiple choice, yay! Okay, so we have a block slides to the right across a horizontal floor. So we have a floor here, I'm just gonna give it a little design. We have a block here, and it slides to the right. I'll just change it like that. Slides to the right. A person called Ted exerts a force T to the right on the box. So this is T, something like that. A person called Mario, or Mario, I guess, however you pronounce it, I pronounce it Mario, exerts a force M to the left, okay? So that's M, which is half as large as the force T, so M equals 1/2 T. Given that there is a friction F, so I'll use orange for that, lowercase f, and the box accelerates to the right, rank the sizes of these three forces exerted on the box. Okay, so all of these forces point in the x direction, so let's sum the forces in the f direction. And there is some acceleration because we are given that it accelerates to the right. So let's just say this is the positive x direction, this is the negative x direction. So we get T minus M minus F equals MAX. But since we know that there's an acceleration, it's pointing in the positive direction, that means the acceleration is a positive value and M is a positive value. So that just, we can simplify this a little bit just to say that it's greater than 0. So that tells us T is greater than M plus F. But we also know that M is 1/2 of T. So let's substitute that in. And then we can subtract, and we'll get 1/2 T is greater than F. And by backward substitution, if we just plug M back in here because we happen to get something back, we learn that F is less than M. Okay. Now we just need to see what's going on with t. Well, we know m is a half of t, so clearly m is less than t. So that, if we just put everything together, we get f is less than m from here, and from this part, we know that m is less than t. And that is our answer, which tells us A is the correct answer. Nice, so another kind of easy question. Cool. So this one seems a little bit more complex. We'll take a very quick break so I can hydrate myself. Yeah, hopefully this section has been interesting. I think friction is a lot of fun. Yeah. So we'll get back into it just now. And let's look at this next question. Question 7. We're nearing the end. So we have two identical blocks of weight W, so this is kind of similar to the question we saw just moments before with two blocks, but something's different here. They're placed on top of each other, shown in the diagram. One block is tied to the wall. Whoa, that's crazy. And the lower block is pulled to the right with a force F. The coefficient of static friction between all surfaces in contact is mu. What is the largest force F that can be exerted before the lower block starts to slip? So that means, like, basically before the lower block starts to move. So first, let's figure out what are the surfaces in contact. Well, we have this surface here with the ground, but also in between these two blocks. They're in contact, so that's where mu is. So, kind of complex what's going on here. Okay, I'm just gonna, I'm trying to change things up a little bit. That's not working. Okay, so let us try to figure out what is going on with the free body diagram. So I'm just gonna redraw the diagram, and we're gonna draw the forces on top of the diagram, which is not a good idea, but it helps for visualization. So we have this block here, and another one here, and there's this force here which is provided to us. And we know that this has mass W, or weight W. I'll just call it W1 and W2, and we know W1 equals W2. Alright, let's work with the bottom block first. Actually, I'm just going to change the labelings a little bit. We'll make the top one W2, bottom one W1, and then that still holds. Okay, bottom block. Gravity, pointing downwards. Normal force pointing upwards, and I'll use the subscripts there. We have F being applied to it, and there's also a frictional force, right? Because it's in contact with the ground here. So that's that block. Now let's look at the second block. There's a normal force, because it's on top of a surface. There is a gravitational force. And what else? Anything else? Yes, there is. There's a frictional force, because there is a surface here in contact. And even though the bottom object is being pulled, the top object still feels that frictional force. You can think about it like when you slide something across a table. It's not just one object feeling the slidiness. It's both objects. Okay, so we have quite the crazy free body diagram here. Lots of forces to consider. But let's just define some axes quickly. This is positive x, this is negative x, negative y is down here, positive y is up here, right? Something like that. And what's the direction of interest? Really, it's the x direction. So what happens when we sum the forces in the x direction? Well, let's see. We have F minus F sub F1. This is F sub F1 minus F sub F2. And that equals MAX. But remember, we want the force right before the lower block starts to slip. So right when it gets starting to move. So that's similar to the sled problem that we did, I believe. Was it the sled problem? Yes, it was. So we're going to do the same thing that we did there, where we create this inequality where it's greater than 0 because acceleration is positive, mass is positive. So we just sort of want that. So what's FF1 and FF2? FF1, this is the friction considering both weights on the ground, right? Because that is this bottom surface right here, and both weights are contributing to it. So I'll just write friction considering both weights on ground. Right? So that tells us that FF, we can use mu times F sub n. But what is F sub n here? Well, that's the normal force if we were to consider one massive combined block. Because now we have that contact with the ground. And here we would have Fn, we would have Fg. So if we sum the forces here, we get Fn minus Fg equals 0, Fn equals Fg equals mg, but the mass is equal to 2w times g, right? Because that's 2w. So, with that logic, this goes to mu times 2w. And that's FF1. So then FF2 is friction of top block on bottom block. So now when we do FF equals, or FF2 equals mu times F sub n, now we're only looking at the top block, just this one block here. And we can see that in the y direction, it's not accelerating, so the acceleration is 0, you sum the forces, we get like F, sum of Fy equals 0, Fn2 minus Fg2 equals 0 implies Fn2 equals Fg2, right? That's mg, or not even mg, that's just w. Yeah, so that is equal to, at the bottom, mu times w. Right, and now we go back to our inequality. F minus ff1 minus ff2 is greater than 0, so this tells us f minus 2 mu w minus mu w is greater than, that's a bad symbol, 0. So f minus 3 mu w is greater than 0. So we want f to be greater than 3 mu w. Right? And if we take a look at the answer choices, we see that that is C. Nice. So this had something similar to the previous question where there were two blocks on top of each other. We considered things as a system right here, with the first force of friction at the bottom, because it relied on both of the weights. But then we considered things individually. For FF2, it was just on this surface, so the normal force only applied to the object on top of that surface. So that's why we considered it individually here. Nice, moving onwards. This is the second to last question, the penultimate question. But unfortunately it has subparts, so may not be the best news. So you have a system shown above, one block of mass m1 that's on a rough horizontal table, rough horizontal table. So that tells us that there's some friction here. Sometimes I just like to put those lines there. The string that attaches it to the block of mass m2 passes over a frictionless pulley of negligible mass. So that means basically we just don't really have to worry about the pulley too much. The coefficient of kinetic friction, mu k, between m1 and the table is less than the coefficient of static friction, mu s. So first they want us to draw and identify all the forces acting on the block of mass m1. Alright, that should be doable. So, first and most importantly, Fg points downward. Gravity makes sense. M1 is on a flat surface, so there's Fn pointing upwards, perpendicular to the surface. M2 is pulling M1 down, perhaps, but there's a string there, so there's got to be a force of tension pointing in that direction. And lastly, we have that there is a frictional force because it's a rough table and that opposes motion. So that points to the left. Now we want to find the minimum value of mu s that will prevent the blocks from moving in terms of m1 and m2. So the technique we're going to use here is something that we did last week, where we bent our axes a little bit. We said that this is the positive direction, and in this direction would be like the negative direction. And we can do this because that is the path that the objects travel in. It's the direction of travel. So we bend our axes a little bit. But first, let's just look at these masses here, and let's draw in some of the forces that we came up with. We had Fn here, we had Fg here, we had Ff here, we had Ft here. But let's look at M2, what's going on here. Fg, I'll label that with a 2. And then we have Ft, 2 pointing that way. Okay. Let me add a page. Alright, so we need to do something about figuring out how the blocks are moving. So that relates to acceleration. And in fact, we want the acceleration to be 0. We don't want the blocks to move. So acceleration relates to summing the forces. So let's sum the forces. And I'll just say, like, not even in the positive direction. Let's just say F total equals ma, right? And the acceleration relates to the direction of travel, which is our bent axes, per se. And, well, okay, let's sum the forces pointing in the positive direction and subtract the ones pointing in the negative direction. So we begin Fg2 is pointing in the positive direction, and then we work upwards. Ft2 is pointing in the negative direction, so let's subtract that. Ft1 is pointing in the positive direction, so we add that. Oops. And Ff is pointing in the negative direction, so we subtract that. And you might be like, well, what's going on with Fn and Fg1? They're not pointing in that direction. They're pointing in the perpendicular direction. They're pointing along the other axes. They're not pointing to, like, with or against the direction of travel. So we don't really care about those. And remember, we said that we don't want the blocks to move, so their acceleration should be 0. So that, let's just say that equals 0. And we should remember something similar from last week, in that we claim that Ft1 equals Ft2, because they're a part of the same string. So this simplifies a little bit, because these terms cancel, and we get Fg2 minus Ff equals 0. Yeah. So Fg2, I'm just going to rewrite it down here. Fg2 is just m2g minus mu Fn, Well, okay, what's the friction? The friction is up here, and that relates to M1. So this normal force relates to M1, and we want that to be 0. Right? And what are we solving for? We're trying to solve for mu. Well, we have M2, right? Because we want it to be in terms of M2. G is fine, that's just a constant, we can keep it. We need Fn1. Alright, so let's take a look at just M1. And Fn is pointing in the y direction, so let's sum the forces in the y direction. Well, the block's not moving in that direction, so its acceleration is 0, so the sum of the forces should be 0. So Fn is pointing in the positive y direction, we'll just say this is negative y direction. So we subtract Fg1, that equals 0. So Fn equals Fg1, that equals M1g. So let's substitute that back in. We get M2g minus mu M1g equals 0. And now we can do a little bit of algebra to solve for mu. We get mu equals M2g over M1g, and that equals M2 over M1. I think that's pretty cool. The coefficient of friction depends solely on the masses. Pretty much nothing else, not even gravity, just how massive these objects are. So yeah, that is part B. Unfortunately, there's still a part C and D. So let's take a look at what's going on here. The question is the same, but now if we look here, the blocks are set in motion by giving M2 a momentary downward push. In terms of these values, determine each of the following: magnitude of the acceleration of M1. Well, we're doing something similar that we did in the last problem, except now the acceleration is not 0. So we'll do the same thing where we sum the forces, and that'll equal m times a. But really, I'm gonna make this capital M times a. Because when we were summing the forces back up here, we were considering the system as a whole, right? Both of these masses are moving together. Even though the forces may be exhibited on only one of the masses, we were saying that the thing was moving as a whole because they're connected by a string. So this mass here, this capital M here, that is equal to the sum of the individual masses because we're considering it as a system. So now we're just going to reuse the equation from before, Fg2 minus Ft2 plus Ft1 minus Ff, but then these canceled, so really these are the forces that we're looking at, Fg2 minus Ff. That equals big M A. Alright, and then it's very similar to what we did before. This is M2G minus mu Fn1 equals, I'll just expand this out, A. And then we can solve. A is equal to something over M1 plus M2. This M2G is fine, it's in terms of M2. Minus mu Fn1 was the same as M1G. So that's that, and that is our answer. It's in terms of all of the constants we wanted. Alright, and now the more daunting question, in my opinion. Now we want the tension in the string. Okay, so for tension, I'm just gonna draw some of these forces back in. Fg2, this is Ft1, this is Ff, this is Fg1, and then up here is Fn1. We said that Ft1, rather the magnitude of it, is equal to Ft2, so to find the tension we just need to find one of these, and I think looking at this second block here is a lot easier because we only have two forces to deal with. So that's what we'll do. We'll sum the forces for block 2. Right, so this gives us, in the positive direction, Fg2 minus Ft2, that equals m times a. And rather, this is m2a, because we're just looking at one block now. Alright, well, this equals m2g. I'm just going to remove the subscript because we're just solving for tension regardless. m2, and well, what's acceleration? Well, we just solved for it. That is this massive expression here. So let's substitute that in. m1 plus m2. Right? Yeah, I'm just going to make this an implies symbol so we're not confused. Now it just comes down to algebra, solving for ft. So we get m2g minus ft equals m2 squared g minus mu m1 m2g, all of this over m1 plus m2, and let's just isolate for ft. That equals m2g minus m2 squared g minus mu m1 m2g, all of this over m1 plus m2. It's fine to leave your answer like this, but we can simplify this further, so let's do it just for practice. What we're going to do with this term is multiply the numerator and denominator by m1 plus m2. Let me just write that out. m2g times this fraction, which is equivalent to 1. And then this term comes along for the ride. m2g, all of this over m1 plus m2. And then we can do a little bit of distribution in the numerator. m2 squared g, all of this over m1 plus m2. Minus m2 squared g minus mu m1 m2 g, all of this over m1 plus m2. So now we create one large fraction because the bases are common. m1 m2 g plus m2 squared g minus m2 squared g minus mu m1 m2 g. This cancels with that. Alright, we're getting there. ft equals m1 m2g minus mu m1 m2g, all of this over m1 plus m2. And if we're feeling fancy, we can even factor this a little bit, and this is common to both terms, 1 minus mu. And that is our answer. I think I may have forgotten, oh wait, this is a plus sign here. Right, because this negative distributes into there. And that is our answer. So, actually it wasn't too bad of a problem. It just, we did a lot of algebra that we didn't need to. So we can leave our answer like this, in that form. The AP exam will be okay with that. But if we wanted to simplify, we have that option too. Awesome. Now we move on to the last question. I assure you, this is the last question. It just happens to have 4 parts. Alright, so we're dealing with an empty sled. Lots of sled talk today, even though it's just the beginning of October. Perhaps I should have made it like Halloween themed, but even then I would be 3 weeks too early, so bear with me. Empty sled, 25 kilos, slides down a muddy hill. Muddy hill indicates that there's friction. Constant speed, 2.4 meters per second. Slope is inclined 15 degrees with the horizontal. We have a nice figure. Calculate the time it takes the sled to go 21 meters down the slope. Okay. Alright. Well, first question's not too bad. It's traveling at a constant speed. So we just say that velocity is 2.4 meters per second. It's 21 meters. The slope is 21 meters. So let's just say that's some delta x quantity. That's a displacement. Time is question mark. Well, I know very well that velocity equals delta x divided by time. So time is delta x divided by velocity. So this is telling me that 21 divided by 2.4 should give me the time that it takes to solve it, to get down the hill. 875. That's our answer. So we were tossed an easy one. That's just a kinematics problem. Alright. And this one should hopefully be equally easy. We're just creating a free body diagram. So, let's see. Gravity points straight down, as it always does. Normal force, perpendicular to the surface. Friction, muddy hill, and it's opposing the direction of motion. Is there anything else? Gravity, normal, friction, tension. There's no tension. No other external forces. Should be good to go. Now we need to calculate the frictional force on the sled as it slides down the hill. It's a little bit more complex. So let's just bring it down here. I'll redraw the free body diagram. Something like, let me first create the slope. Get rid of this. So yeah, we have Fn pointing perpendicularly. We have FF pointing backwards, and we have FG pointing downwards. So this is a question where we need to shift our coordinate axes, because if we keep the normal axes, then we run into issues that the direction of motion is not in the direction of one of our axes. So we'll create a shifted perspective, and we'll just say that this is the positive x direction and this is the positive y direction. Okay, cool. So now we have to do something about our FG because it is still not in the right components. So let's just extend this a little bit, and we can see that we have this triangle that represents the slope. And while we were given the angle of the slope is 15 degrees. So this is 15 degrees, which means that's 75 degrees. So that's 15 degrees. So let's just sort of redraw what's going on. We have these like axes here. And then let's just only look at FG. FG is pointing this way. And we want this FGX and FGY. And we'll draw in some perpendiculars. I guess let me change this FX. FGX. Right? So that's that. This is 75 degrees. So this is 15 degrees. So we'll keep the 15 because that's the angle that we were given. And yeah. Alright, so let's start by taking the sine of the angle. Sine of this, opposite is this side, which is the same as FGX. So FGX divided by hypotenuse is that, which is FGX. This tells us that FGX equals FG sine of 15 degrees. 15. Similarly, let's take a look at the cosine. Not quite sure what I'm writing. Adjacent to this angle is FGY, so we will write that down. And divided by the hypotenuse, which is still FG, we get FGY equals FG cosine of 15 degrees. Alright, cool. So now we have a modified free body diagram. Let me create the axes first. Right, so something like this, where this is the direction of motion. I'll just abbreviate that DOM. I've never done that before, nor has anyone else in physics, so it's not a good habit, I suppose. Fn, Fgy, this is Fgx, and we have friction opposing it. Cool, so all of that work just to now calculate the force of friction. So friction's pointing in the negative x direction, because that's the positive x direction. So let's take a look at what happens when we sum the forces in the x direction. Well, let's see what's going on here. In the positive x direction we have Fgx, negative x direction we have Ff. What is Max? Well, if we scroll back, we see that the empty sled is sliding down a muddy hill with constant speed of 2.4 meters per second. Wow, who knew that kinematics would come in handy? What does constant speed mean? When velocity is constant, we know acceleration is equal to the change in velocity divided by change in time. So that means it's equal to 0 divided by the change in time. So our acceleration is 0. And mass times acceleration would be 0. Cool, and we're solving for Ff. So if we add that to both sides, we simply get Ff equals Fgx. And well, we just solve for Fgx up here. That's equal to Fg sine of 15 degrees. And we know that is equal to mg sine of 15 degrees. And we were given everything here. The mass of the sled was 25 kilos, gravity 9.8, sine of 15 degrees. We can simplify that a little bit to get 63.4 newtons. And that's our answer to that. So that's quite the force of friction, but that should kind of make sense, right? 25 kilo sled, friction is opposing the motion. We think back to the reindeer that was pulling a 30 kilo sled, similar angle, but that was with the motion. So, I mean, should be feeling pretty good about that answer. And now I assure you, this is the last subpart of the problem. And the prompt for the problem is the same, so we just need to look at D, calculate the coefficient of friction between the sled and the muddy surface of the slope. Okay, let's see what's going on here. Well, we just solved for the force of friction, right? The frictional force. And we want the coefficient of friction. But we know that the force of friction is related to the coefficient of friction because it's equal to the coefficient of friction times the normal force. So if we find the normal force, we can just solve for mu. So let's scroll back and take a look at our free body diagram. And here we see that if we take the sum of the forces in the y direction, that should equal 0, because the sled isn't accelerating in that direction. So we get Fn minus Fgy equals 0, and more importantly, Fn equals Fgy. Well, what's Fgy? That is this right here, Fg cosine 15. So Fn equals Fg cosine 15. That's equal to mg cosine of 15 degrees. So using that logic, we say that Ff equals mu times mg cosine of 15 degrees. Now let's solve for mu. Ff divided by mg cosine of 15 degrees. And now we have everything. We just solved for Ff up here. That is 63.4. So let's substitute that back in. Equals 63.4 divided by mass of the sled, 25 kilos. G, 9.8. Cosine, 15. I don't really know what that is off the top of my head. That tells us mu equals 0.27. That's our answer, and that's the last question of today. So yeah, we explored a lot of friction today, but friction is a super important force. Yeah, it's just as important as gravity, just as important as the normal force, just as important as tension that we've talked about. But so we've really covered 4 very, very important forces. So yeah, I think that's basically it for today. We learned quite a bit about what composes friction, that we need the coefficient of friction, we need the normal force, the product of those gives us the force of friction. We learned about kinetic friction, we learned about static friction. We learned how to approach certain problems. If we have an incline problem, we probably need to shift our axes. If we see a problem with 2 or more blocks, we have to consider the system as a whole, as well as things on individual levels. Use the formulas that we know. Sometimes we need kinematics. So yeah, those are some of the lessons we learned today. So yeah, hopefully this lesson was helpful. And yeah, we will be back in just a couple of days with a new lesson in physics. So that'll be on Monday. And then Wednesday we'll be back to calculus and normal scheduling. So that will end today's lesson. So hopefully that was enjoyable.